Hey, welcome back. So this is the first real section of the course, and we're kicking it off with something really important, something big. It's called Big O notation. And when I say big, I don't mean that it's long or difficult even. It's big in significance. It's something that I had no choice but to start the course off with this topic because, at least if I wanted to make it a good course, because it's going to come up in, I won't say every single video, but maybe 70% of the videos in the rest of the course. Don't hold me to that, but a lot of videos, a significant number. We're going to refer back to what we talk about in this section. So before I even explain what it is, I have a quick warning. There's a bit of math in this section. And I'm warning you not to scare you away, but actually to encourage you to push through it if you do struggle with math, or if you're someone who hasn't heard the word logarithm ever or in 10 or 20 years. That's going to come up in this section at the end, but don't panic, because what we're going to do here in this section is establish a framework for talking about code in the rest of the course. And that does involve some math up front, but it means that the rest of the course isn't going to be, some of it will be mathy, definitely, but this is not indicative of what the rest of the course will look like. So just push through it. If you like math, great. If you have some problems with this section, just remember that the entire course isn't like this. And we're just getting it out of the way because, like I said, it has to come first. I don't really have a choice. Okay, sorry if I scared anybody there. Let's talk about the objectives for this section. So in this video, we're going to start by just talking about the need for something like Big O notation. I haven't even mentioned what it is, so we're going to get to that. Then we're going to describe what it is, so why we care about it, what it is. We're going to learn to simplify Big O expressions. We'll define time complexity and space complexity. We'll evaluate time complexity and space complexity of different algorithms using Big O notation. And then we'll describe what a logarithm is, a bit of math at the end there. So I know it's a lot, but we're going to start with this first bullet point. Motivate the need for something like Big O notation. So what is the idea here? Well, this course is about algorithms, it's about solving challenges, it's about computer science and data structures, but for every topic in this course, there's 10, 20 different implementations or solutions that could work, probably way more. How do we know what's best? So let's scale it down a bit just to a single problem. Let's say that there are two valid solutions to a problem. They both work, and they're different, not just in names or variable names or something, but totally different in approaches. One uses a loop, the other uses, a list or a string or something to accomplish the same task. How do we know which one is best? That's really what Big O is about. It's a system, it's a way of generalizing code and talking about it and comparing code and its performance to other pieces of code. Okay, so here's a more concrete example. Write a function that accepts a string input and returns a reversed copy. If I asked you to do this, which maybe some enterprising students will do this and come up with some creative solutions, off the top of my head, I can come up with 3-ish solutions, different approaches, and I'm sure there are way more out there. I actually found this post on Stack Overflow that has 10 different implementations in JavaScript, and they're all different. Like I said, it's not just a different variable name. It's not just switching a for loop for a while loop. There are different approaches. How do we know if all of these work? Here's one using a for loop and an array. Here's one that uses no loops and it's no arrays. It's all, actually, I guess there is an array in there at one point, but it's all built-in methods. How do we know which one's best? Well, we'll get there. But wouldn't it be nice if there was sort of a system for classifying code or for comparing it, which I've already spoiled it and said that's what Big O sort of is. Think of it sort of like if we're talking about earthquakes. If this was a seismology 101 class, very early on, I would start off by talking about the Richter scale, because then that allows us to talk about earthquakes and compare them to one another, so that instead of just saying, oh, there's a big earthquake and then a bigger one over there, we can say there was a 7.5 and then a 9.2 over there. And that puts things into context. It's kind of not a great analogy, but the idea is that we can assign labels, generalized labels to our code. So instead of saying something like great or or awful for our code, we can have a numeric representation of the performance of code. So that's what Big O is going to give us. Rather than colors and text like great, it's going to look a little bit different. It might look a little mathy, but it's actually pretty straightforward once you get past the first hurdle of it looking very foreign and weird. So one last point I want to make, some of you might be wondering, if I asked you to write a function that reverses a string and you get it to work, doesn't it only matter that you get it to work? Like, why does it matter what's best? The solution you come up with is the best. And in some ways, I think that depending on your project and the context, that's true. The best solution is the one that you can get to work. But when we're talking about things like interviewing, technical interview, code challenges, or working at a large company where you're working with a huge data set, let's say hundreds of millions of pieces of data, where one algorithm implementation could save an hour every time it runs compared to another implementation. Performance matters at that point, and there is an actual best algorithm or best solution. So it's important to have a precise vocabulary to talk about how our code performs. So even if you're content with your solution to something, it's helpful to be able to understand how it compares, how it performs compared to others. It's also good for discussing trade-offs between different approaches, because often it's not as cut and dry as I made it seem. It's not that one solution is always great and the other one is always terrible. Sometimes one solution might be great at handling really large data sets, pieces of data. Another one might always be very consistent in the time that it takes, but it might take more time up front. There's trade-offs, so it's not always just this is the best. Also, if you're trying to debug your code, it helps to understand things that are slowing it down. Not just looking for errors, but let's say that your code is working, but for some reason it's taking a lot longer than you expect, or your computer is lagging and freaking out in the browser when you execute some function. It helps if you understand some of the things we're going to talk about in this section in Big O notation. You can actually pinpoint where some problems might arise. So it helps us identify inefficient points. And then finally, you should care because it comes up in interviews a lot. A lot of times an interviewer will say something like, tell me the big O of this algorithm or of this function that you've written, or here's 3 functions, what's the big O? That will make sense in a bit, but it's important just to know for interviews. I said it's less important because hopefully you're learning it to actually understand things and to help you understand your code better and talk about your code better rather than just directly trying to master it for an interview. But interviews are important, so no judgment there either. So I'm going to leave this video off here. I'm trying to keep things more compact. Don't want any rambling videos. In the next video, we're going to pick up with a real example, some code, and start to analyze how efficient it is. All right, so let's take a look at a more concrete example. Let's compare 2 solutions to the same problem. All right, so here's our problem. Suppose we want to write a function that calculates the sum of all numbers from 1 up to and including some number n. So if we plug 3 in, we should get 1 plus 2 plus 3, which is 6. The most common, or the easiest to come up with solution, this is the one that comes to my mind first, is to basically create a total variable, an accumulator, and loop through all those numbers and add them in one at a time, starting at 1 all the way up until n. So that's what I've done here. We have a for loop, total variable starts at 0, and at the end we return total. We start the loop at 1, we go up until n, each time through, total plus equals I. Okay? And I actually have, there we go, I have it open as a snippet here. If you're not familiar with snippets, basically it's a way for me to just, rather than copy and paste code into the console and have to deal with losing it and rerunning it and that pain, in Chrome, you can go to the Sources tab, and then there's a Snippets tab you can click on, and it allows you to create new snippets. I have a couple of them here, and I'm going to use them in this course quite frequently as an easy way to save code and execute it. And just to show you how it works, here's the same add up to function, and I'm printing it out at the bottom, the result of adding up to 6. So that should be 6 plus 5 plus 4 plus 3 plus 2 plus 1. To execute it, I can either click over here, or you can see the shortcut it suggests to me on a Mac is Command Enter. It will say the correct shortcut on a PC. I think it's Control Enter. So if I do that now, I get 21. If I did it with 3, or yeah, there we go, I get 6. If I did it with 100, I get 50/50. Okay, so that's just to demonstrate that that works. Next, there's a second solution. There's more than these 2, but these are 2 that I'm going to use because they illustrate my point. This one is definitely less intuitive. As you can see, it's a lot shorter. It's a single line, which doesn't necessarily make it better, but it's very different. There's no loop involved. What we're doing is it's more of a mathematical formula. We take n and we multiply it by n plus 1 divided by 2. And where this is derived from, I'm not going to go into. I do have slides on it, or a slide that talks about how we arrive with this formula. If you want to check it out, you can, but it's not the focus of this video. So I don't want to distract from the actual focus, which is evaluating and comparing these pieces of code, not actually diving into how we write them. So just to show you this one, it does work. I have another snippet over here. I can run the same thing. Let's do it with 6 again. And I'll do Command Enter to execute, and I get 21. And just to walk through what happens there, it's the equivalent of taking 6 plus 1 first, which is going to give us 7. And then we multiply that by 6, which gives us 42. And then we divide by 2, which gives us 21. So it does work. It gives us the same answer in the end. Again, how it works, we'll leave that be. All right, so we established there are 2 working solutions. Which one is better? And of course, the first thing that we could ask is, what does better actually mean? Does it mean the faster code in seconds or milliseconds? Does it mean the code that's fastest when we're adding a small number versus a large number? Let's say we want to benchmark it at when we add up all the numbers between 0 and 1 billion. Is that a good test? Or is it about how much memory is used? Is it, the number of variables that are created, the data that is stored each time that function is called? Or what about something like readability, legibility? How important is that? Is that better? Or brevity, that's not on here, but a lot of people care about that. They like to minimize the length, the number of characters used in their programming. Not my style personally, but definitely valid. All of these are valid concerns, and it really comes down to the situation. But I think most people would agree that the first 2, especially for now, we're going to focus on speed. We'll come back to memory usage in a bit, but these 2 often can be more important than something like readability. And unfortunately, they often come at the expense of readability, and that's sort of the balancing act of writing good code, is writing efficient code that doesn't use up a ton of memory, but also is still readable and doesn't look like complete gibberish. So we're going to talk about basically how all of these play together throughout the entire course. It will be a recurring theme. But we're going to focus on evaluating speed, how long code takes to execute. That's where we're going to start. So how do we do that? Well, the simplest way would be to use something like built-in timing functions, something like this, where we have our first add up to, and then I use a function or a method called performance.now, which in the browser is just going to tell me the number of milliseconds since the document was created, basically since I opened the window. And then so I'm going to save that to a variable before I call add up to. Then I'm going to call add up to with, what did I do? Is this a billion? I think it's a billion. So I'm going to call it with a large number. And then after that finishes, I'm going to check performance.now again, which should have incremented a bunch of milliseconds, most likely. So I have 2 numbers. Then I just subtract them, the second time minus the first time. And I divide it by 1,000 because it's in milliseconds and I want to work in seconds. We don't have to do that last part. And I print it out. So this should work. And I actually have a snippet right here. Same thing. So add up to our same one from before. And we're calling it with 1 billion. And we're going to print out how long elapsed. Let me clear my console first. And I'm going to execute it. There we go. 1.2575 so on seconds. Let me do it one more time. And what you'll actually see, I don't think I executed it, there we go, is that it varies. So it changes. Even on my own computer, nothing really has changed. Right? I haven't added code, I haven't changed the numbers here. It's the exact same code, but we're getting a different output. Before I forget, let's go over to this second solution. So the exact same number, let me just make sure I didn't leave off or add a 0. Yes, they are the same. And I'm doing the same thing, taking performance.now at the beginning and performance.now at the end. I guess I should show what that looks like. You can see that it's kind of a large number at this point because I've had this open for a number of minutes. If I refresh the page though, which I just did, now it's at 2,000 milliseconds, which is 2 seconds. And now if I did it again, we're at 6.6 seconds. And if we subtract the 2, it's 4 seconds roughly in between. Anyway, we're doing the same thing here. Okay, so now if I run this, you you can see we get a way smaller number. But it's still, actually, I guess it doesn't look like it's changing here, is it? The measurements, the differences are too small, really to capture. But my point is that this is significantly shorter in duration with the same data as this one. Here we go, 1.24 seconds compared to basically 0 seconds. So that seems like a good sign for this solution. It seems like it's much more efficient, and that's great. But this process, it's not the most reliable of manually timing things like this before and after and comparing it to the other function. And it's not that easy for us to talk about. How would I actually write down, how would I give it a label of how efficient this one is compared to this one? Is it based off of the percentage of speed? Is it do I subtract the number of seconds or milliseconds? It gets a little blurry. This brings us to the problem with time, which I'm reserving for my end-of-life memoir title, The Problem with Time. It's just a nice little, sounds very deep. So the first is that different machines will record different times, so it's not reliable. Depending on the specifications of a machine and what's currently happening on that machine, what code is running, the results you can get will be different. That doesn't really mean that we'll get the opposite results where the first solution is suddenly faster than the second one, but it means that the margins could change. The actual measurements could be different and are almost guaranteed to be different times. And as we saw, the same machine will record different times. So in my browser, I just did the exact same code, that first example, and it differed each time by a little bit, which isn't really a problem, but it still shows that it's not precise and that we can't rely on that. And second of all, or third of all, I guess, is that for fast algorithms, things that are happening on a really, really fast scale, speed measurements might not be precise enough. We have 2 or 3 or 4 algorithms and they're all super fast and they're doing something very quickly. There still is one that is going to be fastest or most efficient. But if our timing functions can't figure it out because they're, the smallest interval of time that can be measured isn't good enough, then it doesn't really help us. So how do we walk through our code and actually talk in general terms about which code is better without having to go and time it? So I want to be clear, I'm not saying that timing your code is a bad idea. I do it all the time. What I'm more saying is that it would be cool if there was another way that didn't involve having to set up a new file and actually go through the process of timing our code. What if our code takes, an hour, something massive, and I'm comparing it to another version that takes 4 hours? I don't want to have to run a test to figure out which one is faster. We want to be able to assign a value to, in general terms, talk about how code compares to other code without having to go through all of this. And that's where big O notation comes in. And that's coming up next. Cliffhanger, sorry. Okay, well, we talked about the problems with using time as our way of comparing code. So if we're not using time, what should we do? Well, it's a very similar thing. Rather than counting the exact seconds that it takes for code to run, which can change so much, what we can do instead is count the number of simple operations that a computer has to perform, because that remains constant no matter what computer we're on. So if we just simplified it like crazy and said that, this one algorithm has 5 operations to run and the other one has 7, it doesn't matter what the specifications of my computer are or the mood that my laptop's in that day. The time we get might be different, but the times will always be determined by the number of operations. So we can use that rather than the exact times. We can just focus on the number of simple operations the computer has to perform. So what I mean by simple operations, if we take a look at this example, the shorter one-line version that was faster, we've got a multiplication happening. We have, after that, an addition, so that's another operation. And then we have a division. Things like the number 1 or 2 aren't operations. The computer doesn't really need to do much there, at least compared to multiplication, addition, and division. Those are operations. So there are 3 operations, and it doesn't really matter what n is. If n is 2, or if n is a billion, there's only 3 calculations that are happening. So 3 simple operations regardless of the size of n, whether it's small or massive. If we compare that to our other solution, the first one, this one has a few more operations. So let's start here. We see a plus sign, which we saw in the last video, and we counted that as 1 operation. But there's a difference here because this is in a loop. So if n is 5, we're adding 5 things. So that's 5 operations. If n is 20, there's 20 pluses. If it's a billion, there's a billion pluses. So it's not just one operation anymore. It's n operations, n additions. And actually, it's more than that because the equal sign is it's an assignment. Now, I hope you definitely shouldn't get too bogged down in the details of counting every minute operation because, as you'll see in a moment, all that matters is the general terms of things, a very, very fuzzy overview. So this distinction doesn't really matter. But to be clear, yes, this is another operation, and it happens as n grows. There's more assignments that happen. So quickly running through these, we've also got this here. So plus plus is shorthand for I plus equals 1. So there's a plus in there, and there's an equals. So 2 simple operations. However, they happen 1 time each per n. That's not a good way of saying that. They happen more as n grows. So if n is 10, we've got 10 additions and 10 assignments. If n is a billion, we've got a billion. So they scale with n. Then up here, we've got 1 assignment. So this only happens once because it's not in a loop. It happens 1 time at the beginning. And then we also have this here. This is a single assignment. I equals 1. That happens once as well at the beginning of the loop. We start with I equals 1. And then we've also got comparisons here. I less than or equal to n. And that is n comparisons again. If we're dealing with 20, this loop runs 20 times. We compare I to n 20 times. So yeah, counting these operations can be tricky. Overall, how many would we say there are? If the previous one, there was 3 operations, what do we say about this one? I mean, it's not a static number. It's not a constant number like 3. So how do we generalize it? There's a lot of ways of counting it and of arriving at an answer, but it could be as high as 5n plus 2, right? 1, 2, 3, 4, 5 plus 2. So if n is 10, we've got 50 operations plus 2 that are outside the loop, so that means 52. That's one way of doing it, but what I want to say is that it doesn't really matter because regardless of the exact number, whether it's 5n plus 2 or 2n or 3n or even 50n, it doesn't matter because what we care about is a general trend. And this is what we're going to see a lot with Big O. We're focused on the big picture. So in this case, as n grows, the number of operations grow roughly in proportion with n. All right, so we finally actually introduced the term Big O. We've basically been talking about Big O without actually saying the term Big O notation. So let's reveal it now. So Big O is just a way of formalized fuzzy counting. It allows us to talk in a very formal way about how the runtime of an algorithm grows as the inputs grow. That's it. It's a way of describing the relationship between the input to a function or as it grows and how that changes the runtime of that function, the relationship between the input size and then the time relative to that input. So we don't care about the other details, only the broad trends. So we've already been talking about broad trends. We talked about, okay, as n grows here, in this first solution down here, it doesn't matter. It doesn't impact the time that it takes. But in our second solution, which is confusingly called add up to first, as n grows down here, the runtime also grows in proportion, roughly in a linear 1-to-1 pattern with n. So that is Big O, what we've been talking about. We just haven't actually been using the correct label. So here's a bit of scary text. We say that an algorithm is Big O of f of n if the number of simple operations the computer has to do is eventually less than a constant times f of n as n increases. It's a bunch of gibberish, really. What it's saying, though, is that there's a bunch of these. I'm just going to put them all out here for now. There's a bunch of options. If you haven't seen this notation, by the way, this just means a function with an input of n and then the output. So we're describing the relationship between the input and then the runtime. So it could be linear, meaning that as n scales, the input, the runtime scales as well, which we've already seen. It could be something different. It could be quadratic, where as n grows, the runtime square is related to the square of n. Or it could be constant, which we've already seen as well. As n grows, it doesn't really have an impact because runtime is always constant, which we simplify down to 1. Or it could be something entirely different, and we'll get to some of these other options later on in the course and later in this section. You can always come back and just think about it as when n grows, as an input grows, what is this chart going to look like? Is it going to grow roughly proportionately with n? Is it going to be constant? If we had a square, it would, be a lot steeper than this. One thing I want to highlight is that when we talk about big O, we're talking about the worst case scenario. So we're talking about basically the upper bound for runtime. So let's revisit our examples from earlier. This first add up to, where we only had 3 operations, and it's constant. It's always 3 operations. So the line we looked at was this one down here that roughly is constant. Remember, in the real world, it's not. It goes up and down a little bit, and runtime does vary, but overall the trend is that it's flat. So we could say that this has a big O of 1, and this is the notation that we'll see. So when you see a big O and then in parentheses, you see 1 or you see n or n squared or n log n or log n, things we haven't gotten to, that is telling us that as n grows, as the input to this function grows, in this case, it has no change. It's not reflected in the runtime. But if we take a look at this one, add up to n, same name, this was the one that had a bunch of operations that are happening where we said that it grows as n grows, the runtime grows, basically in a 1-to-1 ratio. The number of operations is eventually bounded by a multiple of n. It doesn't actually matter if it's 1n or 5n or 50n, because at the end of the day, we simplify it down just to n. And we're going to talk about the rules for simplifying these expressions. But basically, we're concerned with just the order of magnitude. So we don't care if it's 5n or just plain old n. It's the same when we're charting it on a massive chart and we're zooming way out and we're just carrying in a fuzzy way, I guess is what you would say. So here's another example we haven't seen. It's called count up and down. And all that it does, I'll just copy it over. I don't actually have a snippet for it, but let's just plug in 10. Okay, so our output is going up 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. At the top, going down 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Back down. All right, so if we were trying to figure out the big O for this function, we'd start by saying, all right, so here, as n grows, we have roughly n operations. We have a loop, so there's big O of n here, because this, as n grows, this loop grows. Same thing down here. As n grows, this loop grows. It's just doing the same thing in the other order, going back down. So you might think that the big N is 2n, but remember that we don't care about that. We care about the big picture, so we simplify it to big O n. So if we go back to our performance tracker, I do have count up and down added in here. So let's plot it out with 100. Let's do 1,000, 10,000. And you'll see, I think that's the last one I'll do. It's taking a while. The next one will take forever. There we go. And you can see there, we get that chart that we discussed. This is the big picture of anything that has big O of n. And we have one more example. And this one's different. We haven't seen this yet. So we have a nested loop. So what it does, it's called print all pairs. And if I plug in 5, it's going to print every pair of the numbers 0 to 5. So it'll be 0, 0, 0, 1, 0, 2, all the way up to 5, 5. And I won't show you the example, but you can trust me, that's what it does. And there's 2 loops. And just like we discussed with the loop, this loop is based off of n, this first one. So that's big O of n, right? As n grows, this is going to be n number of operations, roughly. But then we have a nested loop, which is also the same thing, O of n, which just means that as n grows, this loop, the number of times it runs grows as well. But this is not O of 2n, which simplifies to O of n, because it's nested. And that gives us something else. An O of n operation inside of an O of n operation is O of n squared. So what this means is that as n grows, the runtime roughly grows at the rate of n squared. So that's a pretty significant difference. And if we plot it out, which we will in just a second, you'll see that. But hopefully that makes sense. I don't know why I paused there. Hopefully that makes sense why there's such a difference. Because if we step through this, if n is, let's just think about the number of pairs. If n is 2, we have the pair 0, 0, we have 0, 1, then we have the pair 1, 0, and 1, 1. So there's 4 pairs. But if we increase n to 3, all of a sudden we have 9 pairs. I won't go through them all, but it increases very quickly. If we increase to 4, we've got 16 pairs. So I said I wouldn't do this, but I added it into my console, print all pairs. If we do 2, there you go, we get the 4 pairs. If we do 3, we get a lot more, 9. Now if we go here and plot this, print all pairs, I'm going to start pretty small and do 10. I'm not even going to go to 100 right away. Let's do 50. Now let's do 100. Let's do 120, 150. All right, so you can see what we're working with here. And I'll try 200. It might take a little while. Okay, I'll leave it at this. This is a different overall trend, a fuzzy version of the chart. We're not looking at a linear thing where as n grows, the runtime is roughly proportionate. It's proportionate to n squared. So as n grows larger, the runtime grows even larger. It grows n times n larger, roughly. And just to show you this, if I increase this to 300, it's going to take a lot longer. And I think I was playing around with 500 earlier, and that was about as much as my computer browser wanted to do at the time. Oh dear. Okay, so there you go. You can see that this, what used to look very steep, now that we've added in 500, it doesn't look so bad, and now it looks really steep, which is the exponential curve. Remember that it's just a generalized way for talking about how efficient an algorithm is. As an input n grows, how does that change or reflect in the runtime? So we've seen a couple of options. We saw add up to first, which was basically big O of n. As n grew, the output, the runtime grew relative to n. Then we had up to second, add up to second, which was constant. It always took roughly the same amount of time. Then we had count up and down, where it was the same as add up to first. If n grows, if it triples, then our runtime is roughly going to triple. And then finally we saw print all pairs, which was our first quadratic, O of n squared, where as n increases, the runtime increases roughly at the rate of n squared. So I'm hoping I didn't lose you there. If I did, well, we have some exercises after this. Hopefully it will help out a little bit. I recommend that you play around with that tool, but be careful because if you plug in super large numbers, it will take forever and or crash your browser window and you'll have to quit that window. Just a word of warning. All right, welcome back. So now we're going to talk more about simplifying big O expressions. We've already seen a little bit of this. I'm going to rewind. Here we go, a couple slides back. If you remember this slide, where we talked about how counting all these different operations can be tricky and that it doesn't really matter the exact count. All that we care about is really the general trend. And so we simplified this from 5n plus 2 to just n. We said that as n grows, the runtime grows proportionately with n. And it doesn't matter if it's 2 times n or 10 times n or 1,000 times n. The trend, the line that we're drawing on that chart, is proportionate with n. So now we're going to talk about some actual rules we can use to help us when simplifying these expressions. There are some helpful rules of thumb that we can follow. Rule of thumbs? Rules of thumb? Rule of thumbs. Okay, whichever one it is. These rules are consequences of the definition of big O, once again, that we only care about the broadest, fuzziest, big picture view. So constants don't matter. So if we have something like O of 2n, we simplify that down just to O of n. O of 500, we simplify that just to O of 1. Because O of 500, remember, is just, that's basically saying there are 500 operations every time, no matter what n is. And so that line, that chart, is going to be flat. And instead of saying it's going to be flat at 500, we'll just simplify it down, saying that it's O of 1. That's how we say something is constant. Constant runtime. O of 13 n squared. Well, we don't need that constant. We just do O of n squared. Because the difference, when we're looking at this, basically if our graph went all the way to infinity as far as n, and we're looking at the difference between 13n squared and just n squared and 1,000 n squared, they're all going to look very, very similar. Once we elongate that chart to that level. So it doesn't really matter. So we just get rid of them because now we can compare these and we know that, okay, this is going to be faster than this and this is going to be the slowest just based off of the charts, the general fuzzy trends. So smaller terms also don't matter. The constant's out front in front of n, but smaller terms like this, O of n plus 10, just get rid of the 10, just O of n. Or in this case, O of 1000n plus 50, we can simplify that just to O of n. We don't need the constants, and we don't need the small term at the end. Now, how about this one? N squared plus 5n plus 8. Well, once again, look at it from a huge, like imagine we're in outer space looking at this chart, and we have to figure out what really matters. What's the trend? At the end of the day, 5n plus 8 is meaningless compared to n squared. When we're dealing with a number, like if you just plug in the number 1000, 5 times 1000, 5n, gives us 5,000. But n squared, 1000 times 1000 is 10 million. I think I did that right. So if we're talking about 10 million plus 5,000 plus 8, just as an example, the difference between 10 million, 5,000, and 8 versus 10 million is so small. And that's just when we plug in 1,000. But now imagine we plug in a billion for n. That difference is going to be meaningless from the big picture view. So we just simplify it down to O of n squared. So a couple things that you can keep in mind. When analyzing complexity with big O, things get complicated and you can nitpick and stress out about the individual details. But there are some rules of thumb, again, that can help. And they don't always work, but it's a good starting point. The first is that arithmetic operations are constant. So if we're adding something or subtracting or dividing and so on, that's going to be constant time. It doesn't really matter the size of the number. Your computer takes roughly the same amount of time to do 2 plus 2 as it does a million plus 2. Variable assignment is also constant. So your computer takes roughly the same amount of time to make a variable, x equals 1,000 compared to x equals 20,000 or a million. It's roughly the same. Accessing elements in an array using an index. So if I have an array and I want to find the first item or the 10th item, as long as I use the index, or I'm working with an object and I have a key that I'm using to access data, that's constant runtime as well. The next rule is that in a loop, the complexity is the length of the loop times the complexity of whatever happens inside the loop. So if we're working with a loop that's looping over a list, or it's looping through, like we did earlier, 0 to n, as n grows, that loop grows. But then whatever happens inside that loop is also consequential, because if we have nested loops, as we've seen, then we end up with potentially n squared runtime. So again, you don't need to memorize these, but it's just nice to, I'm going to throw them out there so I can come back to them. So let's see a couple examples. Here's a new function. It's called log at least 5. Let me just copy it over. I paste it in, and if I call it, I pass in a number like 10, and it's going to log 10. But if I plug in 1, it prints 1, 2, 3, 4, 5. So all that it does is it prints numbers up to n, but at a minimum, it prints 1, 2, 3, 4, 5. So if I give it 3, we still get 5. But if I give it 7, we get 7 printed out. 1, 2, 3, 4, 5, 6, 7. So what's the big O here? How would we categorize this? So we have a loop, and this loop is going to go from 1 to either 5 or n, whichever one is larger. So we could worry about the 5, but we only really need to worry about that as n is small. And what we care about is what happens as n grows larger. So as n continues to grow and grow and grow towards infinity, what happens to the runtime? Well, if n is 10 million, this loop is going to run 10 million times. This 5 doesn't matter. So we can just simplify this and say that the big O of this is O of n, because as n grows, the number of operations grows in proportion with n. So here's another one. This is the opposite. Log at most 5, paste it in, and if I try, there we go, at most 5, if I plug in 30, it still only gives me 5. If I plug in 3, it gives me 3. So it's going to take whatever is smaller. If I give it a large number, if it's larger than 5, it's only going to log 5. If I give it something less than 5, then it will log. It's also important, it's only with positive numbers. So if I give it 0, it doesn't do anything. And that is important to note because as n grows here, it kind of doesn't matter because we're going to take the min, which is 5. So if n is approaching 1,000, this loop runs 5 times. If n is approaching 1,000,000, the loop runs 5 times. If n is 2, then the loop runs 2 times and 3 times. So the graph would actually look like, 2 and then 3 and then 5, and then it would stay static at 5. And we can simplify that by saying that as n grows, which is what we care about, the big O of this is just constant. It's O of 1. So rather than O of 5, remember we can simplify that down and say O of 1. So if we were to plot both of these out, what we see, the general trend, is something like this, where, I forgot I have all those little transitions. We can ignore all these other ones. We haven't talked about things like log n and n log n, but what I've done here is just put them all on a chart. So we can see, first of all, O of 1 is a flat line. And that's great. If we can have runtime O of 1, that is fantastic to have constant runtime. It's pretty rare when we're dealing with some more advanced algorithms. Something like O of n, it's okay. You can see the general trajectory. It's much better than something like quadratic n squared runtime. So when we have something like log at least 5, as n grows this direction, the runtime is also going to grow. And when we have at most 5, the second one, which we said had constant runtime, as n grows, once we get past the first little 1, 2, 3, 4, once we get past the first 4 and we approach infinity, n is going to always be 5, which we just say n is always constant. So I know that this is a lot, and some of you might be struggling with it, and that's to be expected. What I think is most important going forward is that if I say something like this algorithm that we've just written has a runtime of O of n squared, that you could identify that that is not as good as something like O of n, for example. And I could show you this chart, but I just hope that you can understand after the end of this section, we're not done yet, but by the end of this section, what it means when I say that something has O of n or O of 1, constant runtime, and how that compares to some of the other options. And like I said, we haven't gone over all of these yet, so we'll get there. Next up, a couple little exercises simplifying expressions. All right, welcome back. So now we shift gears a little bit, and we're going to talk about something called space complexity. Everything we've talked about so far, we've been worrying about time, about how fast algorithms run, what the runtime is. That's called time complexity. We've been analyzing the runtime of an algorithm as the size of the input increases. Now let's talk about what happens to the space that an algorithm takes up as the size of the input increases. So we can still use big O notation for the same thing, use the same formal syntax for describing what happens, but now we're going to focus on space, the amount of memory that's taken up. So there's some basic things we have to get out of the way. One is that obviously as n grows, if we're approaching infinity, the size of the input itself, which is n, is going to grow. So we're going to ignore that part. You might hear the term auxiliary space complexity if you do some research, if you read Wikipedia or something. That refers to the space required by the algorithm only, not including the space taken up by the inputs. That's what we're going to talk about. We care about the algorithm itself because our n is growing. That's in big N or in big O. That's kind of the point. We're going to say that as n grows, we assume that the input n is going to grow. So let's not care about that space. Let's care about what repercussions that has inside the algorithm. So unless otherwise noted, when we talk about space complexity, technically we're talking about auxiliary space complexity. Hopefully that's not too scary, but basically it just means we're focusing on what happens inside the algorithm. So some basic rules of thumb. The first is that most primitives, things like booleans, numbers, undefined, null, and JavaScript, are constant space. So it doesn't matter what the size of the input is. If the number is 1 or the number is 1,000, we can consider it constant space. It doesn't matter if a boolean is true or false, it takes up the same amount of space. Strings are a bit different because they require O of n space. So if n is the length of the string, if we have the input grows to 1,000 characters, well, that's a bad example. If it grows to 50 characters, the string takes up 50 times more space than a single character string. Same thing with reference types, arrays, and objects. So generally, we're talking about O of n, where n is the length of the array, or the number of keys for an object. There's not really a length technically, but so if the length of an array is 4 compared to another one that is 2, it takes up twice as much space as the shorter array. So let's take a look at an example. So here we're focusing on not time complexity, we're focusing on space complexity. So this function called sum, it takes an array and it just sums all the items in the array. So we have a variable total starts at 0. Then we have a loop that goes from 0 to the end of the array, and we're just adding in the value of each item in the array to the total variable, and then we return it at the end. So again, space, not time, is what we're concerned about. So what are the things that take up space? Well, no matter what the array length is, we have one variable called total, one number. And then we're looping through, but we're not concerned about the time again. And then we have a second declaration inside the for loop, let I equal 0. So that's another number. And that's it for space. We're coming back to the total variable, we're adding into it, but that doesn't matter. That takes time, but the space is already there. So no matter what the size of the array is of n, or in this case ARR, as it grows, it might be 1,000 items, it might be 1,000,000 items, well, it might be 10 or 50 or 1,000. Let's start with simple. It doesn't have an impact on the space that's taken up because we only have these two variables and they exist no matter what. We're not adding new variables based off of the length. We're adding to the total variable, but we're not making a new variable. So that really just means we have constant space, O of 1 space. It's always the same, no matter the size of the input. Here's another one. So this is called double. It takes an array, and well, why don't I just copy this one and show you? So I've copied it in, and it's called double. I'll pass in an array of 1, 2, 3. What does it return to me? An array with 2 items. What am I saying? An array with the 3 items, the same length, but each one has been doubled. And what's important to note, it is making a new array. So it starts with making that new array, then it loops over the length of the first array, and then it multiplies each item and pushes that on to new array. And then it returns new array. So what does that mean for the space complexity of this? As the array length grows, as the input approaches infinity, let's ignore the fact that JavaScript can't handle that, what happens to the space that this algorithm takes up in here? So yeah, we have this, where we're going to make a new array no matter what every time. But that's not that significant when we consider this right here. We have this new array, and it's getting longer and longer and longer directly in proportion to the length of the input. So if the array is 10 items here, we're storing 10 items in a new array. If this is 50 items, we're storing 50 items here in a new array and returning that. So the space that's taken up is directly proportionate to n, to the input array. So n numbers, we get O of n space. So we don't need to care about things like this. We can simplify it down just to the fuzziest level, which is O of n, rather than O of n plus 1 or something like that, or actually plus 2, because we also have this. Those don't matter. So I know it's a lot, and it's hard to understand right away, and it might not click. That's okay, though. We have some exercises, but I want to make it clear that you do not need to master this before we move on. I should just, the whole point is that I should have, in 10 sections from now, we'll have a couple solutions, and I want to be able to say, hey, the space complexity of this one is great, and the time complexity of this one is terrible. N squared time complexity, but constant space complexity or something. And you should hopefully be able to understand what I mean by that. Hey, welcome back. So I said at the very beginning of the course, we had a little math. The whole section's pretty mathy, but this last video in particular is condensed with some math. We're talking about logarithms, as you can see. Whether you learned about logarithms at one point, or you learned about logarithms at one point and forgot it all, or you never learned about it, I'm going to try and just make it pretty simple and also quick, because it doesn't actually matter that we're masters with logarithms. The reason I'm even showing it to you, I guess that's where I should start, is that some algorithms that we'll see have a big O that isn't simple. It isn't big O of 1 or of n or of n squared. These are very common complexities, and we've seen them, and I think they're pretty easy to comprehend, hopefully. But there are some big O expressions that involve some more difficult math or less common expressions. And something that comes up more than I personally would like are logarithms. So that's why I'm showing it to you. We will have, and I'll show you in a bit, some algorithms in this course where their time complexity, instead of being O of n, might be O of log n. So let's start with what's log? What's a logarithm? So put simply, a logarithm is the inverse of exponentiation. So just like division and multiplication are a pair, logarithms and exponentiation are a pair. So here's what you might see. You would read this as log base 2 of 8 equals 3. And what we're really asking or calculating here is 2 to what power equals 8? So if we take 2 and we raise it to some power, what power will give us 8? 2 times 2 times 2, it gives us 8, so the answer is 3. So 2 cubed equals 8. Here's just that same thing written down again. Log base 2 of a value equals the exponent. You can switch it around and say 2 to the exponent equals value. Just like if we had 1 divided by 2 equals 0.5, you could switch that around and say that 2 times 0.5 equals 1. We can move things around. They are the inverse, exponentiation and logarithms. Now, logarithms aren't always working with base 2. You could have log 3 of something. 3 to what power gives us 8, or log 5, or log 10. The most common ones, though, are the binary logarithm, which is log 2, so 2 to what power. Then there's also the base 10, so 10 to what power gives us some answer. Then there's also log e, which I'm not going to go into, but I probably shouldn't have said that anyway. There's a third very common algorithm. However, for what we're concerned about, we care about the big picture, and we're going to omit the 2. We're just going to say log, because first of all, it's annoying to write all this. Is this subscript? I think it's subscript, not superscript. It's annoying to format this, but also it doesn't really matter at the end of the day, because if we're comparing the graph of a constant time and a quadratic time and log n time, it doesn't really matter if it's log base 2, log base 3, log base 10. It's going to be the general trend that we care about. But just so that we're clear, this isn't actually a mathematical operation on its own. You can't just take the log of a number. You need to have a base. So we need to say log 2 or log 10. But in the slides and in literature, that sounds stupid, in literature, in things that you'll see online around big O notation, the shorthand is just log. If you want a rule of thumb, just to calculate it roughly, the binary logarithm of a number roughly measures the number of times you can divide that number by 2 before you get a value that's less than or equal to 1. So if we have 8, we're going to divide it by 2, and it's still greater than 1. So we're going to divide by 2 again. It's still greater than 1. Divide by 2 again. Now we hit 1. So that means 3. We divided 3 times, so the answer is 3. 25, however, it doesn't go cleanly. There's no way of dividing it by 2 evenly. So we divide by 2, and by 2 again, and again, and again, and then we're finally below 1. So this tells us that it's 1, 2, 3, 4, somewhere between 4 and 5. And the answer is 4.64. So the actual calculation is not that important. What matters here is if we take a look at it on a chart. So logarithmic time complexity is great. If you have an algorithm with log n time complexity, I'll show you which one it is here. Here we have constant time in red. And then right above that in orange, we have big O of log n. You can see that up front, it's a little steeper, but then it really tails off and is very gradual. And this is great. If you have an algorithm with log n time complexity, fantastic. So that's why I'm showing it to you, because it compares very favorably to things like O of n. There's another common one we'll see, n log n. I'm not going to go into examples just yet, but both of them involve logs, so I figured I should show you. It's not as good, but it's still better than something like n squared, the quadratic time complexity. So really the point at the end of this section, even if you're stuck on some of the math, what I hope we have is that later in the course, I'll show you 2 algorithms. I want to be able to point to one and say, this one has log n time complexity, this other one has O of n time complexity. And I hope that you can look at this chart and understand that, cool, the first one is better. It's at least more efficient, it's faster, because log n is much better than O of n. The larger n gets, it doesn't grow that much, the runtime. with log n, but it grows a lot in proportion with n for O of n. Okay, so that's why I'm introducing it here. We have a bigger picture of these are the most common big O expressions. Like I said, the math, we don't have to worry about too much, but I just wanted you to know what a log is. Let's talk about where this will come up. So certain searching algorithms do have logarithmic time complexity, and we will see those as we go and progress through the course. Also, efficient sorting algorithms involve logs. So not all sorting algorithms, but some of the more efficient ones do. So we'll see that as well. And then finally, recursion, another topic. So basically there's 3 reasons here, none of which we've actually discussed. So this might not make a lot of sense. I'm basically saying in the future, we're going to see it at this place, and this place. Searching algorithms, efficient sorting, and recursion. And that has to do with space complexity with recursion, not time. So hopefully these will make more sense once we get there. Really, again, it comes down to just having this nice picture here. If I was teaching this in a classroom, I'd have this up on the wall at all times, like laminated, printed out, and I'd have a long stick, and I'd whack it on the wall and point it for every algorithm, point at one of those lines. And I'm going to try and kind of do the same virtual thing in this course online. Okay, so let's do a quick recap. We covered a lot. To analyze the performance of an algorithm, we use big O notation. It has to do with big, high-level, big picture trends. As the size of an input grows, we want to know how the runtime changes or how the space complexity changes. So big O can give us a high-level understanding of time or space complexity. It doesn't care about precision, just general trends. Time and space complexity as measured by big O depends only on the algorithm, not on the hardware. So yes, the actual time it might take to run one algorithm on my computer compared to some supercomputer will definitely be different. But the general trend won't be. Big O is basically measuring the number of operations that happen, whether an operation takes 10 milliseconds on my computer or 1 millisecond on another computer, which that's pretty slow anyway, but ignore that. And big O notation is everywhere, so we're going to get a lot of practice, and that's why it's coming first in this course. I feel kind of bad about it, like I've said before, because it's not the most welcoming topic, and it's kind of a rude awakening, but it gives us a context to discuss things. I'm going to go back to that terrible analogy of the Richter scale with earthquakes. It gives us a way of discussing how earthquakes compare their magnitudes. It's the same idea. We can compare algorithms now and say, oh, this one's great, this one's terrible, because its space complexity is X, or its time complexity is X. Anyway, let's call it a day here. Let's stop now, and we'll see you in the next section.